Hi, for those who have chosen this to do this problem, this is called a linear array. This is a 24 element linear array of dipoles, each oriented along the z-axis. You gotta change that. It's gonna be actually oriented along the y direction because for reasons that EasyNet considers the ground plane to be the xy plane. So um, to actually have a ground plane, um, uh, for this case we're gonna have a ground plane, so we're gonna use the xy axis, just because EasyNet doesn't have a capability to have a ground plane on the, for example, YZ axis. Okay, so the dipoles are placed a distance of d from each other in the x direction and center at the origin. Okay, so that's how the problem describes. Then what you're gonna do is calculate the pattern of the dipole and its image. So if you and you're gonna assume the dipoles are short and with a sine theta pattern. This is gonna be the element factor. So what you're gonna do is like you got a ground plane and you're gonna have the element factor. So this is gonna be basically your derivations of your equations, which I'll explain in another video. But it's basically gonna be two dipoles. Um, Actually, you're gonna like cascade those 24 dipoles, and it's gonna have an image. So it's gonna be image of the 24 in one side and image of the 24 in the other side. So it's gonna be two elements actually, and you calculate that element, that array factor. Okay, and then you're gonna calculate the array factor for the 24 element. So that's gonna be the equation that it's being on the book, the the actual like normal equation for uniform illumination. Um, so you're gonna be having actually two array factors and one element factor, and then you're gonna plot a cut in the um, x and y plane. What it's actually gonna be, yeah, x and y plane. The distance between each element on the array of 24 dipoles is 0.7 lambda. You're gonna calculate the directivity and the 3 dB beam width and the locations of the first, second, and third nulls, and the side of the side lobes, nulls and side lobes. So that you can do based on the equation, um, that equation that's on the book. Then you're gonna inject a phase into the array in each element that will create a 45-degree angle pattern. So let me describe a little more about this. Okay, so here's uh, the model that I'm describing. So you got like 24 elements. The distance between the elements is gonna be 0.7 lambda, and the height of the 24 dipoles about the ground plane, it's lambda over 4. In I Just to get you started, I created the first element points here. So this is considered the element 1. So element 1 is right here. So element 2 is, it's gonna be next to it. So you could see the difference. I mean the trend. And then just one thing to mention here: we're using half lambda dipole, so we're gonna use the length of the dipole 0.25 and 0.25. That's the two ends. So if you add those, the length of the dipole is gonna be 0.5 lambda. Oh, this is a mistake here. This should be 0.7, the distance between the dipoles. And you're gonna end up with for part 8, you're gonna end up with a plot that looks very similar like this. So you're gonna have a main beam here and side lobes here. So you'll be able to get the values of these the side lobes and where the nulls occurs. So you can calculate. Well, you'll be able to calculate it on the theoretical equations, and then you're gonna be also be getting the values of in here in EasyNet, and you'll compare both of those answers. To actually create steer the beam 45 degrees, you gotta calculate the angle that you need to rotate, that you gotta inject in each element. So in order to inject the phase in each, you gotta calculate first the phase, and then you gotta come to in sources and start creating the phases, injecting in each element incrementally. Okay, and then if you do that, then you'll end up with a plot that looks just like this, more or less. Okay.